All right. Hello, class. Um, Mr. P here with bugs. Um, Bug is not feeling very well, and I can't figure out what the deal is. He keeps crying, like making a yippee sound, and just at like random times. It's like he's getting a sharp pain or something, and I don't know what the deal is, but it's bothering him today, clearly. And he's not a very happy doggy today. So he's being really sensitive. Um, he's always a sensitive doggy, but and he's doing a weird pant, which if you know dogs, you know that panting can sometimes mean stressed out. So this is a stressed out pant from Bugs. So I don't know what the deal is, but he was running around yesterday playing, and then today he's. Whoa, what's that? Is that a little doggo? Is that a little doggo outside? Is that a little doggo outside? Woof, woof. But yeah, he's being really sweet though. He just wants to be close to someone. Be close to me. Oh, Bugs. Oh. So I'm gonna put him back here and hope he just lays down. Lay down, Bug. Lay down. Lay down. Lay down. Go on, sweet boy. Good boy. What? Lay down all the way. What the heck are you doing? Lay down. Where do you want to go? You want me to take you someplace else? Oh. Yeah. There you go. All right. So I realized yesterday that I actually did the wrong pages. I assigned you guys some pages for circular motion and gravitation, and I had meant to do the pages for circular motion and gravitation, but I did energy instead. I just misread the two columns. So I'm going to do circular motion and gravitation today. Let's see, who we got today? Hey Sebastian, hey Kyle, hey Vicky. So I'm going to be doing pages 62, 63 first. And okay, so it says Angela is in a stopped car at a traffic light when the light turns green and she accelerates. Okay. Sketch and label vectors for velocity, acceleration, and net force on the car. So the car is going forward. So the velocity is going to be forward. Okay. She's accelerating forward, so the acceleration also points forward. And the net force is also forward. So all three are pointed forward. Which way does Angela feel pushed? So Angela should feel pushed in the direction of the acceleration, right? So Angela is going to feel the back of the seat pushing against her, pushing her forward, okay? So I would say she feels pushed forward. She feels pushed forward because the back of the seat is accelerating her. with the car. As she approaches a stop sign, she slams on the brakes. Sketch and label the vectors for velocity, acceleration, and net force. So she's approaching the stop sign, so the velocity is going forward. However, she's slowing down, so the acceleration is pointing backwards. The net force and the acceleration are always going to point in the same direction, so the net force is also going to feel backwards. So Angela's body feels pushed backwards when the car is accelerating backwards. So this is going to, so what is stopping Angela? It's going to be a combination of friction from the bottom of the seat. It's going to be a combination of the seat belt, and it could also be the feet on the floor. Those three things are going to provide some kind of force that slows Angela to a stop. As Angela continues driving, she rounds a corner at a constant speed. Sketch and label velocity, vector, acceleration, net force. So we know that the velocity is tangent to the circle. We know that the acceleration is in towards the center of the circle. And the net force always points in the same direction as the velocity. So Angela's body is going to feel pushed towards the center of the circle. So one of the things you'll notice is that if you're turning in a car, your body sort of leans to the outside of the turn, and it's the side of the car that pushes against you and keeps you in the circle. Okay. All right. So that's just reminding you guys the directions of velocity, acceleration, and net force in circular motion. So next page I'm doing are pages 68 and 69. Okay, page 68. A car of mass m passes over a bump in a roadway that follows the arc of a circle of radius r, as shown. The dot at right below in the picture represents a car at the top of the hill. Draw a Freebody diagram showing and labeling the forces exerted on the car, the relative lengths of all vectors should reflect the magnitude of the forces. Each force must be represented by a distinct arrow. So we've got normal force pointed up, and then we've got weight force pointed, you guessed it, downward. It's possible we also have a thrust and an air resistance, but I'm not going to worry about sideways forces. An important thing here is that the weight force must be bigger than the normal force. Why? Because the car is moving in a circular arc, and so the acceleration has to point towards the center of the circle, which is downward. So there has to be more downward force than upward force. Okay. Starting with Newton's second law, derive an expression for the maximum speed v the car can have without losing contact with the road. For each line of the derivation, explain what was done mathematically. Your expression should be in terms of r and physical constants. So, what we have is, so the net force we can see is normal force going up and weight force going down. So what I did here is I substituted in the actual forces that are acting on the object. Then what I'm going to do is n minus mg equals m times minus v squared over r. So I plugged in the formula for centripetal acceleration. It is negative because the acceleration is down toward the center of the circle. Okay? Now, if the car is about to lose contact with the hill, the normal force is the force of contact. So if there's no contact anymore, the normal force must be 0. So so I would set the normal force equal to 0. So now I have minus mg equals minus mv squared over r. And so I said set normal force equals 0. This represents loss of contact. And then I would just do algebra to find that v equals g times r to the 1/2 power. Okay? So that's what I would say. In your derivation, you set the normal force equal to 0. Why? So I would say normal force is a force of contact. If there is no contact, there can be no normal force. Okay, part D. It says a truck of mass 2m passes over the same bump. Compared to the car, how many times bigger or smaller is its maximum speed without losing contact with the road? Justify your answer with reference to part B. So one of the things we can see about part B here is that m is on both sides of the equation, so m canceled out. So our final answer does not contain m. So what I would say is that the final answer obtained for max speed does not contain m. Consequently, all, I'll say cars of all different masses have the same max speed. Okay? Or something to that effect. So this kind of problem is called a vertical circle problem. There is a horizontal circle problem where the centripetal force is constant, and then we had a vertical circle problem where some of the forces are changing directions depending on whether you're at the top of the circle or the bottom. Let me see if I have any questions. No questions. All right, so the last two pages I was going to do are 85 and 86. So I'm going to scroll 85 and 86. All right. So it says, a student is given the following set of orbital data for some of Jupiter's moons and is asked to use the data to determine the mass of Jupiter. Assume that these motions are circular. Write an algebraic expression for the gravitational force between Jupiter and one of its moons. So we would have F equals G, mass of Jupiter, times the mass of the moon, divided by the distance between them squared. Use your expression for part A and the assumption of circular orbits to derive an equation for the orbital period t of the moon as a function of its orbital radius. You got it. So what I would do is I would say net F equals ma. That's where everything starts. And I'm going to apply it to the moon. okay? Because we want to know what is the orbital period of the moon, so we should use the moon's do Newton's second law for the moon. The next law I'm going to substitute in the gravitational force for the net force. And we can see that the mass of the moon cancels out. So we get G times the mass of Jupiter over R squared equals A. So now the acceleration is the centripetal acceleration. I'm not going to use the V squared over R expression. I'm going to use another expression that we learned in class, which was 4 pi squared R over period squared. Okay? So then what we do is we just cross multiply, and we get G times the mass of Jupiter times the period squared equals 4 pi squared R cubed. So we called that Kepler's law. So I've just reviewed the derivation of Kepler's law. Which quantities should be graphed to yield a straight line whose slope could be used to determine the mass of Jupiter? Okay, so what if I take this equation and I divide both sides by 4 pi squared? Then I would have Gm over 4 pi squared times period squared equals R cubed. So we want to linearize the graph. So R cubed, what if we let R cubed equals Y squiggle? And then what if we let period squared equals X squiggle? Then what is our equation going to look like? Our equation is going to look like Gm over 4 pi squared times X squiggle equals Y squiggle. Buckets of doggo out there. So we can see that this is a linear relationship, and the number that multiplies X squiggle is your slope. So that would be my slope. So I have slope equals Gm over 4 pi squared. All right. Complete the table by calculating the two quantities to be graphed. Label the top of each column, including units. Looks like they already did that. See how they have seconds squared and meters cubed. So they already kind of did that for me. So I'm going to square these quantities. I'm only going to do the first one and the last one because I only need 2 points to get a line. That's not very good, but just in the interest of time because it's kind of boring. So I'm going to square that, and I get 4. So I get 4.3 times 10 to the 14th for period squared, and then 1.12 times 10 to the 10th. I want to cube that. 1.4 times 10 to the 30th. Okay, so that's my first row. And then now I'll do the last row. So 5.03 times 10 to the 7th. We want to square that. 2.5 times 10 to the 15th. And then 2.02 times 10 to the 10th. Cubed. 8.2 times 10 to the 30th. All right. So now I'm going to graph them. So notice my first point was 4.3 times 10 to the 14th and 1.4 times 10 to the 30th. So 4.3 and 1.4. So that's maybe like right here or so. So yeah, notice how it has times 10 to the 30th already on the horizontal axis, and it has times 10 to the 14th already on the vertical axis. Now for my last one, I have 25 and 8.2. So 8.2 and 25, so the last one is right here. And we can see that I have a, whoa, like that. So yeah, that's what I would graph, and then the slope of that would be GM over 4 pi squared. It looks like it doesn't want me to actually calculate what the slope is. Part F says 2 identical probes are sent to study one of Jupiter's moons. Probe A is in a geosynchronous orbit around the moon, while probe B rests on the surface of the moon and rotates with the moon. Rank the gravitational forces from greatest to least if 2 or more quantities are the same, state so clearly. Okay, so notice how we have, we're going to have some action and reaction pairs here. So just beware of that. Okay, so we've got the force of the moon on probe A, the force of the moon on probe B. Well, the force of the moon on probe B is going to be greater. Why do I say that? Because probe B is on the surface. That's closer to the moon, so the gravitational force is stronger the closer the two things are. The force of probe A on the moon, that is the reaction force to this. Those are action and reaction pairs. The force of the moon on the probe, the force of the probe on the moon. So C has to be equal. Oops. What happened? So what did I say? B was greater than A, but that has to be equal to C. All right? The force of B on the moon is the same as the force of the moon on B. Those two are an action-reaction pair. Why isn't it? Okay. And then the force of the probe on B and the force of the probe on A, these two are action-reaction pairs. Now, because the probes are way less massive than the moons, they're going to have a much smaller gravitational force on each other. So those ones will be the smallest forces. So if I type it out, I have B equals D. Those are two are the greatest. Those are greater than A and C, which are equal to each other. And then those are greater than E, and F. So that would be my ranking, and I explained it while I was doing it. Okay. So those were the pages that I was supposed to do yesterday. So thank you for watching, and I hope you guys have a great weekend. We'll be doing some simple harmonic motion and also like torque and angular momentum next week. Review all that stuff. Your AP exam is on Thursday of not next week, but the week after that. Make sure you check out in the announcements. I posted some information on from College Board on how the AP exam will be taken. And furthermore, you guys are welcome to submit the homework for this week, get some easy points, and then you're going to submit the daily items from last week as this week's quiz. Okay? So please do that by the end of the day today. You can still put 4 names on it. Hopefully there are 4 people that actually helped out. So stay safe out there, and thank you for watching. Those of you who are still striving to learn, I appreciate it a bunch. Bye now.